So Newton's second law of motion, or just for short, N2, is one of the most important concepts that we're going to cover this semester. It is the central piece of Newtonian mechanics, the model for motion that is Newtonian mechanics. And if you remember from the very first chapter we covered, a law is often something that can be written very simply as an equation. So here is what Newton's second law of motion looks like in equation form. Acceleration equals the net force over a mass. So if we write this out in words, then we would say the acceleration of an object, so of an object, is equal to the net force on the object divided by the object's mass. So you'll notice that this is all happening on one single object. You're looking at how the object's motion is changing, its acceleration, and we're looking at the net forces on the object. So these are forces coming from outside. They're external forces, not forces originating on the object. And it's divided by the object's mass, a property it has. So let's dive a little bit deeper into this equation. Acceleration, we're already pretty familiar with that. The acceleration is equal to the derivative of the object's velocity, or the change in how the object moves. The units of acceleration are meters over seconds squared, and really just any kind of change. So it can be a change in speed, or it can be a change in direction, or it can be either of those. So acceleration, something we're already pretty familiar with. Over here we have net force. So the net force, which can also be written as this. So that symbol right there is a capital Greek sigma, which stands for sum. And the net force, as suggested by using the symbol sum, is the sum of all the forces on the object. I'm just going to move that over here, because we actually now, having said that, we need to modify this. Force is a vector, so this, we'll have to remember, is the vector sum, and that's going to mean we're going to want to break things up into components so we can easily do math on it. So direction matters. You got to do things, sort of the x stuff all together, the y stuff all together, the z stuff all together. You can't just add them willy-nilly. So it's actually the vector sum of all of the, and here we need another modification, all of the external forces on the object. That is outside, or forces that come from not the object, from something other than the object. And what else do we know about force? Well, so if we have the forces, that means we're adding up a bunch of forces. Force is the push or pull on an object. You're trying to get it to change its motion either by pushing or pulling on it. It's a vector, which is why we have to do a vector sum on it. And it has units of newtons. And Newton gets capitalized because it is named after a person, so capital N. And this is not a base unit, it is made up of other units, and a unit is made up of kilograms times meters over seconds squared. We rewrite the equation up here as force net equals, just move the mass over to the other side, mass times acceleration. You can see the units work out. Kilograms are the units of mass, meters per second squared are the units of acceleration, and newtons are the units of force. So force, it's a vector, it's push or pull, it has these units. And then finally, mass. Mass mass, which has units of kilograms, which we already used over here in this equation, mass you can sort of think of a property of an object that is its stubbornness. How much it doesn't want to change its motion, how much it resists changing the motion given these forces on it. So again, mass, you can sort of think of it as stubbornness. The fancy physics word for that is inertia. And again, it is a property of the object. So whatever object you've got, it is going to have a mass, and that will follow the object around everywhere. Whereas the net forces, those aren't belonging to the object. They are outside or external forces coming from something else. And then the acceleration is the result of how those two mix. The outside forces that are adding up to be a net force and the mass of the object itself. So let's write down Newton's second law again. We'll use it in the perhaps more familiar form of F net, the sum of all the external forces on an object, are equal to its mass times its acceleration. So the first thing that we should note about here, so NB, which stands for nota bene, meaning note well, caution. Mass is not the same thing as weight. They're really similar. They're connected. We use them interchangeably all the time, but they aren't actually the same thing. The units of mass, as we just said, are kilograms. The units of weight are newtons, because weight is actually a force. So weight is something that acts on an object. Mass is something that an object has. So this is a property of the object. So no matter where the object goes or what happens to it, well, I guess you could chop something off and then it'd be a different object. But as long as the object stays the same, its mass is going to be the same. Whereas weight is a property of the object and the object's location, where it is. So it's both inside, intrinsic to the object, and external, due to where the location is. And that is because the weight is equal to the object's mass times the acceleration due to gravity, wherever it is. If it's on the surface of the Earth, then this g is going to be the one we're familiar with, 9.8 meters per second squared. If it's on the moon, it'll be different. So the weight of an object can change depending on where it is, even though the mass, which goes into the weight, which is why they're so closely related, well, that's going to be the same no matter where it is. And incidentally, another unit that is sometimes used for weight is pounds. So your weight in pounds or in newtons, that is a force. Your mass in kilograms, that is a property of you yourself, not just you and where you are. The second thing to note, if all of the forces that are external to an object, if they happen to add up to 0, well, from Newton's second law, we can say, all right, if the net forces are 0, and it's an object, meaning it does have some mass, so mass is not 0, then acceleration has to be 0. So if this is true, and we're assuming the mass isn't 0, then the acceleration's gotta be 0. And alternatively, if we see that the acceleration is 0, that must mean, so we can do this both ways, if acceleration is 0, then the net forces on the object has to be 0. It's not quite the same thing as saying that there is no force on the object that has acceleration 0. It's just that those forces must be balanced. So one way to put this is you could have a bunch of forces on there. We'll do it with 3 in our example. If we add all of those up to get the net forces, and that's equal to 0, well then the acceleration will be 0, even though there are forces acting on this object. Since those forces all balance each other out, the acceleration is 0. And this is known as equilibrium. An object that has zero net force, when you add all the forces acting on it from the outside up and they add up to zero, then you say the object is in equilibrium. Or in other words, net force is zero, the acceleration is zero, and that means an object in equilibrium is going to have constant velocity. It'll keep its direction, it'll keep its speed. And this is, of course, really what's going into Newton's first law. Newton's first law is sort of a general statement of what's going on in Newton's second law. It's just saying, like, if an object keeps its motion, that is, it stays at rest if it is at rest, or it keeps a constant velocity, that is, its acceleration is zero, this case, then the net force on it has to be zero. And contrariwise, if an object is being acted on by a net external force, then its acceleration can't be zero. So either both of these are zero, or neither of them are zero. And that's Newton's first law, special case of Newton's second law. And that's pretty much what you need to get started on this most crucial part of the Newtonian model for motion.